Welcome back, everyone. My goal here is to dive into the details of exploring how current and emerging exploration methods can help meet the specific challenges of exploring for gold in Ontario. We'll be covering a wide range of tools from geological techniques to geophysical methods to geochemical strategies. And along the way, we'll highlight case studies from Ontario, some examples of success, and others that offer valuable lessons from what didn't work. Then we'll wrap up with some strategic recommendations based on what we discussed, tailored to three core stakeholder groups: technical exploration teams, corporate executives, and investors. And finally, what we're going to do is to bridge the technical with the strategic. Whether you're in the field or in the boardroom, the goal is to give you a clearer picture of how innovation, insights, and smart planning can come together to drive discovery in Ontario. Now, let's take a moment to ground ourselves in Ontario's geological setting, because understanding the geological context is the key to understanding how and where gold forms here. Ontario's gold is primarily hosted in Archean and Greenstone belts, and these are ancient, structurally complex belts of volcanic, sedimentary, and intrusive rocks that formed around 2.7 billion years ago during intense tectonic activity. The vast majority of gold deposits in Ontario belongs to the orogenic gold category, also known as mesothermal gold systems. These are characterized by networks of quartz carbonate veins that carry gold and are closely tied to major shear zone of faults. And these structures served as fluid conduits during the final stage of regional compression and mountain building. In the Abitibi Greenstone Belt, which is the largest and most gold-endowed belt in the province, over 60% of gold is found in late orogenic quartz vein systems that formed during the tectonic events between 2.66 and 2.64 billion years. These deposits are strongly structurally controlled, often lining with major crustal fault corridors like Porcupine-Dexter deformation zones and the Larder Lake Cadillac Fault Zone. Two of Ontario's most famous gold camps illustrated this perfectly. Timmins, with more than 60 million ounces produced, is aligned along the Porcupine-Dexter Fault. Kirkland Lake, which its rich vein systems, sits on the Cadillac Larder Lake Fault. These first-order faults acted as long-lived, deep-rooted channels for gold-bearing fluids, and understanding their geometry and history remains a cornerstone of exploration in Ontario. As the exploration in Ontario matures, we are facing a new generation of challenges, especially as we move into less obvious, more concealed terrains. Firstly, much of the northern Ontario's bedrock is hidden beneath thick Pleistocene glacial sediments like till, clay, sand, and also extensive forest cover. In areas like the northern Abitibi and other underexplored belts, this means we have fewer outcrops, fewer visible veins, and fewer geochemical anomalies at surface. Traditional prospecting and mapping methods simply don't work well here. That forces us to rely much more heavily on geophysical surveys and surface geochemistry, using tools that can see through the overburden and detect hidden mineral systems. Secondly, the depth of remaining targets is increasing. In many Ontario's well-known camps, the shallow deposits have already been mined, and what's left is often down-plunge extensions of known structures or deeper systems entirely. For example, in 58 North Zone at Detour Lake, that was discovered by stepping out nearly a kilometer from the existing pit, drilling along a deformation zone that lay entirely under overburden. These type of targets are expensive to test, so precision in targeting becomes absolutely critical. Thirdly, the economic of what makes the deposits viable have changed. With higher gold prices and advances in bulk mining, there is now a viable market for large lower grade deposits. And these might not have been developed in the past, but can now be profitable as open pit operations. This shift broadens our exploration scope. We are no longer just chasing narrow, high-grade veins. We are also evaluating systems with disseminated or sidewalk mineralization that could support bulk mining. As Dobé and Mercier pointed out in 2020, exploration in Archean terrain like Ontario is evolving. The model has expanded to include syngenetic, volcanic, and intrusion-related systems supported by economic and technological changes in mining. So the bottom line is that we need to stay competitive. Exploration in Ontario must adapt, targeting deeper, subtler, and often less convenient systems using more integrated and data-rich approaches. Now let's discuss how current and emerging exploration methods and technologies can help meet these specific challenges. So in the following, I will discuss the state of art in geophysical surveying, geochemical analysis, and data integration. These are the three pillars of modern mineral exploration. I will emphasize on techniques that have shown practical success or hold particular promise in geological condition of Ontario. When we think of exploration technology, we often picture high-tech tools and softwares, but in reality, the strong geological foundation still drives successful exploration. New insights from regional mapping and academic works can significantly sharpen our targeting efforts. For example, in Abitibi and Wabigon sub-provinces, recent research has reshaped how we understand gold distribution. A synthesis by the Geological Survey of Canada in the Detour Lake revealed that major deposits tend to cluster around large-scale deformation zone and adjacent Timiskaming-type basins. These settings are very similar to those in Timmins and Val-d'Or camps. What this tells us is that the Sonda Lake and Lower Detour deformation zones, despite being poorly exposed under till or swamp, are highly prospective. To apply these insights on the ground, exploration teams are taking a few key steps: structural mapping and core logging, competency contrasts, reappraisal of deposit models. So let's open them up one by one. Okay, the first one is structural mapping and core logging. In area with outcrop, geologists are mapping folds, faults, and shear zones in very detail, sometimes using LiDAR or portable XRF for quick data collection. In drill core, oriented core and televiewer tools let us measure veins and foliation orientation accurately. And understanding the structural evolution, knowing which events like D1, D2, D3 were active during the gold mineralization, can really refine your targeting. For instance, in the Dryden area of Western Wabigon, researchers linked gold mineralization to a major D2 transpiration event. Gold is consistently found along D2 shear zones like Manitou Strait Fault. That tells us to focus on those structures in similar belts. On the competency contrasts, gold often precipitates where soft and hard rocks meet. These units tend to concentrate strain and let fluids in. In the Garrison Gold District, deposits formed where ultramafic rocks are interlaid with rigid dikes along the Porcupine-Destor Fault. That mechanical contrast created complex fracture zones and acted as a trap for gold. So in the field, spotting an ultramafic body in a shear zone or where a dike swarm cuts across a major fault should raise flags. And these are good candidates for follow-up with geophysics and geochemistry. One of the other important steps for exploration team is reappraisal of deposit models. Instead of just looking for classic quartz vein, the exploration team can consider disseminated mineralization in intrusions or even banded iron formation. That means keeping multiple models in mind while reviewing geochemistry, geophysics, and alteration patterns. Hemlo is a good example. Debates around its origin didn't stop it from becoming a major discovery. The key indicator, a broad molybdenum and potassium-rich alteration halo. That's why many teams now run multi-element assays and use portable spectrometer to track alteration minerals in the field. In overall, the geological approach today is more holistic. Mapping of structures, interpreting stratigraphics, recognizing important breaks like unconformities or Timiskaming style basins, and being open to less conventional deposit types. Let's move on to geophysical exploration techniques. In Ontario, where dense forests and thick overburdens obscure the bedrock, geophysics is essential. It doesn't just help us map the underlying geology, it also gives us clues about mineralization. Let's walk through the main techniques we rely on and how they are evolving. Okay, let's start with airborne magnetic. High-resolution magnetic surveys have been a workhorse in greenstone belts. They help distinguish mafic, ultramafic rocks, which are typically magnetic, from felsic intrusion, which aren't. Since 1970, the Ontario Geological Survey has built a strong foundation of regional magnetics. And these datasets show greenstone belts as linear magnetic highs surrounded by quieter granitoid zones. EM conductors, often related to graphitic or sulfide-rich sediments, frequently align with these belts. While these conductors aren't ore themselves, they outline prospective corridors. Today's surveys are flown at higher line spacing and lower elevations, picking up more details like small felsic porphyries or cross faults that could localize gold. Talking about TDEM systems like VTDM offer deeper penetration than older frequency domain EM methods. They can detect subtle conductive features hundreds of meters down, useful for targeting sulfide-bearing alteration zones. A VTM survey in the Wabigoon belt showed that many gold didn't align with strong conductors, but rather with weak to moderate conductors that also had subtle IP effects. So interpretation is the key. A strong conductor might be barren pyrrhotite, while a weaker one on the flank could be more prospective if it fits the geology. Modern systems also record decay curves, which help differentiate between massive sulfide and quick decaying regolite or graphite. These tools help us prioritize targets more efficiently. On the IP and resistivity, IP servers are widely used at the property scale to detect disseminated sulfide, especially pyrite and arsenopyrite associated with orogenic gold. Hemlo is a great example. Despite being a low sulfide system, its subtle IP anomalies helped guide discovery drilling. Modern three-dimensional IP inversions can create volumetric chargeability models that really sharpen our targeting. An area with deep overburden, deep penetrating IP setups or systems like Titan 24 can reach over 300 meters. And while airborne IP is still maturing, some recent surveys are showing promise in mapping chargeability from the air. On the gravity and magnetotellurics, gravity surveys measures density contrast, which can help outline large alteration systems, but they are less common in greenstone gold exploration. MT, on the other hand, can image crustal-scale features. Government MT surveys in Abitibi have shown the gold-bearing faults like the Porcupine-Dester are deep tapping structures, possibly channels for mantle-derived fluids. While MT doesn't resolve shallow targets well, it reinforced the idea that exploring along these major faults makes sense. Seismic reflection is still experimental in hard rock environments, but this is starting to show real potential. In the Timmins camp, a two-dimensional seismic profile by the Metal Earth project imaged the Porcupine-Dester fault at depth and even picked up reflectivity pattern links to mineralized zones. As costs come down, this method might help us map deep ore systems and structures more routinely. About the remote sensing and drones, in forested regions like Ontario, satellite imaging has limited use, but drones are a game changer. They are now used to carry magnetometers and even light wave EM systems for ultra high resolution surveys over small target areas. Drones can fly lower and tighter than traditional aircrafts, giving us much better resolution. And they're also great for structural mapping using photogrammetry or LiDAR to generate detailed topographic and outcrop models. In summary, geophysical exploration has moved from broad regional mapping to focused high-resolution surveys. The key is integration, magnetics for structures, EM for conductors, IP for sulfides, combined and interpreted alongside geology. Today, three-dimensional inversion software allows us to pull all of these together into actionable drill targets. And as drilling advances, borehole geophysics like televiewers and downhole EM are extending our vision into the third dimensions, helping team adjust targeting in real time. Okay, let's move on to geochemical exploration methods. Geochemistry is a key tool in exploring Ontario's greenstone belt, often giving us the first clues to buried gold systems. While the glacier cover adds complexity by dispersing material, it's also spread the geochemical signals over a wider area. Sometimes we can use this to our advantage. In area with thin overburden, soil sampling like humus or B-horizon layers can pick up subtle metal anomalies leaking from mineralized bedrock. Hemlo is a great example where a soil anomaly in arsenic and antimony led to its discovery. In regions with thicker cover, we switched to till sampling, especially basalt till, which can contain gold grains and trace element signatures transported from up ice. The Ontario Geological Survey has built regional till database, and companies often follow up with tighter sampling grids. Modern till works goes beyond just chemistry. we now analyze gold grain counts and grain shapes. Angular grains, for example, suggest the source is nearby. The kind of evidence led to the Borden Lake discovery, where systematic humus sampling in the forested area with no outcrop returns gold values of up to 30 ppb. Follow-up trenching and drilling uncovered a multi-million ounces deposit under 20 meters of cover. Another important step for exploration team is little geochemistry and alteration halo mapping. Rock geochemistry, whether from outcrop or drill core, is another powerful but sometimes underused method. Gold systems often have wide alteration halos with specific chemical signatures. For instance, carbon dioxide-rich fluids can carbonate mafic rocks, while potassic alteration brings in potassium and strips away sodium. In Timmins, studies found that alteration intrusion near gold veins showed low potassium, low strontium, and elevated potassium to sodium ratios, signs of intense potassic alterations. Companies now routinely run multi-element analysis on core using portable XRF or lab-based ICP-MS to pick up on these patterns. Even if gold values are low, enrichment in elements like arsenic, stibnite, or tellurium can show you are in the halo of the system. In Red Lake alteration indices built from rock chemistry and pathfinder elements were among the best predictors of gold, right alongside gold assay themselves. Pathfinder elements are important, and isotopes. Elements like arsenic and antimony are classic pathfinder in Ontario, commonly associated with arsenopyrite and antimonite in gold systems. Depending on the deposit, other elements like tellurium, tungsten, molybdenum, bismuth can also be useful. Hemlo stands out again for its high molybdenum and mercury, which aren't typical in other camps, but were part of its unique fingerprints. Modern ICP-MS techniques can detect these elements at very low levels in soils, tills, and rocks, helping us build a more reliable anomalies. In some cases, isotopic studies add another layer. For instance, sulfur isotope data from island gold suggested a magmatic source for the ore fluids, pointing explorer toward nearby intrusions rather than sedimentary units. And while these techniques are more research-oriented, they help refine exploration models. And finally, geochemical modeling and artificial intelligence. With more data, we are turning to advanced analytics beyond classic tools like anomaly maps and scatter plots. Machine learning is now being used to find hidden patterns. Random forests, neural networks, and weights of evidence models can combine geochemical data with geological and geophysical inputs to highlight targets. These models do best with large data sets. Sometimes that government and legacy databases can help provide. In regional surveys, these tools can distinguish subtle anomaly from noise or help separate a true geochemical fingerprint from glacial dispersion. Still, interpretation is the key, and models must be tested and validated with geology in mind. In summary, geochemical exploration in Ontario has become more sophisticated, moving from single element soil samples to integrated workflow involving surface samples, rock chemistry, alteration mapping, and machine learning. And success depends on careful sampling design, a full suite of element approach, and close collaboration between geochemists and geologists. And when you combine a strong geochemical anomaly with supportive geophysics in the right structural setting, the case for drilling becomes much stronger. That's the support behind many of Ontario's most successful discoveries. The last step for exploration success is data integration and visualization. One of the biggest shifts in exploration isn't just about new tools. It's about bringing all our tools together. Integration is now at the heart of modern exploration. When we combine geological, geophysical, and geochemical data in a meaningful way, we get a much clearer picture of where to look next. That's where GIS and three-dimensional modeling comes in. GIS lets us overlay multiple data sets like geology map, geophysical grids, soil and till data, drill holes, and explore spatial relationships. But we can go beyond just looking at maps. With prospectivity modeling, we can actually quantify which area are most likely to host gold. Great examples come from Red Lake. Harris and colleagues use statistical models like weights of evidence and logistic regression to turn exploration criteria into binary layers and produce a prospectivity map. And it successfully highlighted known zones like the mine trend and even identified new target areas. Today, some companies take this further using machine learning, training algorithms on known deposits and using geological inputs like distance to fault, rock types, and pathfinder elements to predict where mineralization might occur. These methods are especially valuable for large properties when prioritizing targets efficiently is the key. We have already moved beyond two-dimensional cross sections with software like Leapfrog, Micromine. We can build up a three-dimensional model of the subsurface, and these models pull together geohole data, surface geology, and even geophysical inversions. In structurally complex terrains like Ontario's Greenstone Belt, this is invaluable. Visualizing ore chutes, fault geometry, or where a fault cuts across stratigraphy in three-dimensional helps with drill planning. For example, you can trace a known structure down plunge or identify sub-parallel faults that might not have been tested yet. And you can integrate geophysical like chargeability or resistivity volumes right into the model, which can reveal deeper features aligned with surface structures. Collaborative data platforms are important. Many teams now use centralized cloud-based platform to share and manage data in real time. That means new assays or field observation from the bush can be uploaded and instantly available to the entire team, whether they are in the core shack or at the head office. This speeds up decision making and helps anyone stays on the same page. It also improves data quality and ensures consistency across disciplines. Artificial intelligence, as far as I'm concerned, is emerging in exploration, but it's already showing promise. Some companies are using machine learning models to scan massive data sets, including unstructured data like old reports or papers, and suggest potential targets. More concretely, artificial intelligence is being used in core logging. Computer vision models can analyze core photos and identify rock types, veins, or alteration with impressive accuracy. And this helps logging to standardize logging and catches features that might otherwise be missed. In Ontario, where visual clues can be subtle, like weak foliation or a few percent of sulfide, this consistency can really matter. But AI doesn't replace the geologist. It's a tool that helps skilled interpreters test ideas and work faster, not a shortcut to discovery. And in summary, I would like to point out that integration multiplies the value of our data sets. It lets geologists test ideas, refine targets, and collaborate more efficiently. Public data like OGS magnetic surveys or GSC geochronology reports can and should be folded into companies' models. Programs like the Targeted Geoscience Initiatives have generated a wealth of information. The explorer who integrates these resources are the ones who will stay ahead. Okay, now having outlined the toolkit of modern exploration, in the next video, we turn to real-world examples in Ontario that illustrate how these tools and methods come together.